This lesson deals with supplemental problem 310. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems, starting on page 13. In our previous two videos, we took a look at the inverse active and inverse saturation models of the transistor operating in this third quadrant of the IC versus VCE curves. Let's take a look at the last one, which is the cutoff. Just like in the first quadrant, we were going to reverse bias the base emitter and base collector diodes. Let's go back to page 16 of Chapter 3 lecture notes. And we're now going to take a look at operating over here and along this line from 0 on back. What's true when we're operating along here? Well, the base collector voltage is less than or equal to this turn-on voltage V sub BCR on. The current is equal to 0. Along here, the current is also equal to 0. And the voltage is less than or equal to 0. With these three models, we've covered all of the parts of these curves in this third quadrant, just like we did in the lecture 3 notes for this part of it. Let's go back and do the modeling. These are all the conditions we just described. Can we build a model that covers all of these? Well, no, we can cover some of those. Cases of no current are pretty easy. They're just simply open circuits. Our base current, our collector current, and emitter current are all 0. And this model covers more than what we'd like because I can't control the voltage across an open circuit. I have to check, if I assume that this is the correct model, that the voltage across the base collector is less than V sub BCR on, and that the collector emitter voltage is less than or equal to 0. What about the PNP transistor? Well, everything is the same. We're simply going to change the subscripts from base collector to collector base and from collector emitter to emitter collector. We'll turn all the currents around, but they're all 0, so it doesn't make any difference. We've covered three things here. We've covered the three currents being equal to 0. Because these two are 0, their sum would also be equal to 0. And then these inequalities are something we can't guarantee for an open circuit, so we'll have to check for them. You would assume that we're in the inverse cutoff for a PNP transistor. We have to analyze the circuit and solve for the collector base voltage and show that it's less than or equal to V sub CBR on, and that the emitter collector voltage is less than or equal to 0. Let's do an example. We have a one transistor circuit with two 1K resistors, a 3.2 volt battery, and now a half a volt battery. Can you solve for the current I and the voltage V if the base collector reverse turn-on voltage is 0.72, the collector emitter reverse saturation voltage is minus 20 millivolts, and beta R is 4. Assume that you're in inverse cutoff, and then check the assumption. Our first step is to replace the transistor by its model, which is just open circuits between the three terminals. And then we're going to label the base collector voltage and the collector emitter voltage. Label the currents being 0. So I can go around the loop here and solve for the base collector voltage. The rise in voltage is a half. The drop is 0 times 1K plus the base collector voltage. And then the voltage in this direction, because of the current, would be a minus 0 times 1K. The base collector voltage is equal to half a volt. Solve for the collector emitter voltage is this node voltage minus this node voltage. This node voltage is minus 0 times 1K. This node voltage is a plus 3.2, but we're going to subtract that, get a minus 3.2. Our base collector voltage is less than or equal to the turn-on voltage of 0.72, and the collector emitter voltage is less than or equal to 0, so our assumption checks. We can now solve for the current and the voltage. The current I is this base current, which is 0 amps, and the voltage V is this node voltage, which is going to be equal to minus 1K times 0, and that's equal to 0 volts. And this is supplemental problem 310.